Hello everyone, the problem that we're looking at once again today is the USACO 2021 January contest Gold Problem 2 of telephone. A few videos ago, I explained how to solve this problem using that dijkstra's algorithm method. And the algorithm I'm going to be using today to solve this problem once again is the layered graph shortest path. So you can pause the video once again and read through the problem if you don't remember what it's asking. So basically, you're given n cows and each cow has a breed within 1 and 50. And now each breed doesn't necessarily want to communicate with each other, and whether they want to communicate with each other is described by a matrix right here. 1 being they're willing to, 0 being they're not willing to communicate with this breed. And now you're trying to pass a message from 1 to n, or passing a message from ij takes the absolute value of I minus j time to transmit. Now you're trying to determine the minimum amount of time needed to transmit the message. So you can pause the video and once again then see if you can remember how to solve it using dijkstras first. Alright, so as we already knew that the first observation we make from this problem is that every cow, you only have to pass message from this cow to every breed that can transmit message with it. You only connect edges from this cow to the closest to of that breed, because we have proven that that's the optimal, and then we can just connect edges and run dijkstra. However, there's another a bit more complicated method if you can't notice that important observation first. It's called layer graph shortest path. So first, let's think about it. The fact that it only takes I minus j time to transmit a message from I to j means that the time we take is linear, which means that we can kind of do something about it. And now k is only 50. And if you already looked at my problem review for the problem of revamping rows, you should know that when there's a very, very small number of types of nodes there are on the tree, you can consider using the algorithm layered graph shortest path. In this case, k is only 50, so we can actually create a graph with only 50 layers. So let's say k is 3 right now with only 3 breeds of cows. So let's create 4 layers actually with 3 breeds of cows. And now we're going to define these layers as this. So this is layer 0, 1, 2, and 3. And layer I means that cow of breed I, if cow breed j equals I, cow of breed I can pass message freely within this layer. So every cow of breed 3 can pass message freely within layer 3, right? Same with cows of breed 2 and layer 2, and cows of breed 1 and layer 1. So I'm just going to add a few points here, 5 points on each layer. The points we still establish as normal. It's just that now we define the layer as you can only pass on the message to every other cow if you're in your current layer. And layer 0 is the original layer where no cow can pass message. And let's say that we have breed 3 for this cow and this cow, breed 2 for this cow and this cow, and breed 1 for this cow. Alright, so now how do we connect edges for this graph? Well, here's what we're going to do. We're going to connect an edge from the original layer, which is 0, to every cow, but on the layer of their breed. So we're going to connect edges like that for those two because they have breed 3 and that. And finally, like that. And then what we also do is we connect an edge between points. But these edges, instead of like the previous one were the way to 0, the way that these edges are 1. Because we know that to pass a message from I to j means that it takes 1 amount of time. So all of these edges have a weight of 1. However, in the original layer, we can't do that, right? Because obviously the original layer, if you just pass on a message, you just pass from 1 to n. And finally, now that we have edges in and edges between, we have to also have edges out, right? And how do we connect edges out from layers? Oh, first of all, let me clarify. All these edges are going into the layers. So that knowing this, we can freely pass on message between layers because we know wherever this message came from, it came from a point of this breed, right? Because the message can only enter layer 3 through a point of breed 3, only enter layer 2 through a point of breed 2, because no other point have inward edges. And how do we connect outward edges? Well, first of all, let's say that breed 3 is willing to communicate with breed 2. Well, then on the original layer, for every node, we connect an edge from this point to every same point, but on the layer of every breed that this breed is willing to communicate with. So take a moment to process that. So say we know this point has breed 2, right? And then if breed 3 is willing to communicate with breed 2, well then let's connect an outward edge from layer 3 of this point to the original layer of this point. And say if breed 2 is willing to communicate with breed 1, well then this point is breed 1, so then we connect the edge. Actually, I'm going to change the color just so it's less confusing. These are outward edges. So since breed 2 is willing to transmit a message to breed 1, this cow is breed 1, and then we connect an edge between this point on the second layer to this point. And now basically what we're saying is every message can only enter through this breed layer through a cow of this breed and can only leave when this breed is willing to communicate with this breed on the original layer. So now if we just simply run a shortest path starting from point 1 on the original layer and find the distance it takes to reach point n on the original layer, we get the answer, right? Because we know on every single layer, these edges basically makes the rule of you can only go into this layer using this breed, and you can only go out of this layer when this breed is willing to transmit. So every single message that reach the original layer that's not obviously on here must have gone through some series of legal passes, right? And with this graph, we can run the algorithm quite easily. So here is my implementation. Obviously, it is way more complicated than the dijkstra method that I explained a few videos ago, but when you can't make that observation, when you're too dumb for the actual dijkstra, this is the best you can do. And it's not much slower at all. You just need to connect more edges. And now, just like the other program with the layer graph shortest path, I labeled every point on every layer. So num_ij is the label of the point j on layer I. And there's only k layers. That's why we can do this, because k is only 50. So only when the k is small do we have the condition to do this. And now between every single layer, obviously, these are the edges that run between layer with a cost of 1, and all these other edges have cost of 0. Exiting edges and entering edges have cost 0, right? And that's obviously the entering edges, and that's exiting edges. And now we just run a dijkstra, good old dijkstra, and we have the answer, -1, because we have because in the dijkstra, we check a point whether it's visited through whether the distance is 0, but the original point will have distance 0, so now we set the original point to distance 1, so then in the way we know that the point 1 is visited. Well, in the end, we just -1, so we don't have to actually use different visit array. So that's just a little trick you can use here. And yeah, that's it for this algorithm, layer graph shortest paths. You see the code is longer than dijkstra, but it's still quite short, considering that this is a gold problem. And the algorithm, I would say, is really smart. I really like this algorithm because you just connect the special graph, and usually after the graph is done, you just run a most basic shortest path algorithm, and you get the answer to a very complicated problem, just like revamping trails and just like this problem. And now, hopefully, after this video, you know how to solve the USACO 2021 January contest gold problem 2 of telephone, not with 1, but with 2 different methods, both having a very good time complexity of around n log m because we have dijkstras. And yeah, that's it for this video. Thank you for watching. Grind report was, I would say, even worse than yesterday. Today, I didn't get mocked by myself and fail the problem that I did before, like yesterday I did, but today I didn't actually do much. Yesterday, at least, I tried the contest. I almost mocked the contest, even though I didn't. But today, I just did one logo problem. It's not even USACO. It's a pretty old logo problem called the P1514. Yeah, 1525. This problem on logo, which is not even the USACO problem, but it's kind of like it. And I just decided I had to do something. I can't just spend a day without doing a single problem with USACO being 10 days away. But I had other stuff, so I don't have much time to do this. Anyways, yeah, that's all. Thank you for watching.